Hmm. Okay. Hmm. Hmm. Yay. I think I've got it going now. Hello, Ankita. You're the first one on board.
Hi.
I'm experimenting heavily right now with all kinds of new technology.
Oh, okay.
Yeah, I've been lost. I've been lost, and so right now I have let's see, I have this stupid webcam thing. Oh no, this document camera, and it's all getting funneled through a virtual document camera called OBS,
Oh, okay. Yeah.
and it is confusing as heck for me. But because literally there are 3 copies of everything on screen. So if I'm like where am I? What's going on? You'll know what's going on. And there is that piece, and there is Cosmos. Right? Right. Okay, good. Right. So what you see is what I see up in my upper right-hand corner.
Yeah.
And I predict that probably with a half hour to go or so, the battery on my camera is going to die. And then I'm going to have to switch over to the webcam or something, or it'll just be this big blemish over there. And you guys will have to suffer only with my voice instead of my voice in my picture. So, so tell me, Ankita, a little bit about yourself. High
Oh,
school, like what interests you, that type of stuff.
well, I do I do robotics at my school, so I'm part of the high school robotics team.
Oh, really?
Yeah.
I like that. I actually, I'm actually very into Arduino
Mhm.
programming, and I've made a bunch of stuff. Like you could call them robots, but they're more like instruments.
Mhm.
Like I made a spin coder
Mhm.
where you put little pieces on, then you push a button and it spins around. I mean,
Mhm.
it's not super impressive, but I made a box and everything.
Yeah.
And then I made a dip coder and temperature controller and all kinds of fun stuff. But I've never made anything like with like arms and legs, that kind of robot.
Mhm. Yeah.
What sorts of things have you worked on?
So the way we do is like we're part of like a robotics league, so we follow a certain game, and then we build our robot based off of that. So we
Uh-huh.
always try and figure out the best solutions, and we do a lot of engineering stuff, and it's fun. So
Okay, so but like, are you actually building robots
yeah,
or like more
like one robot. Yeah,
oh, okay, cool.
yeah. You
Oh, I see.
program
So
it,
everybody's sort of
and
cooperating.
yeah.
Yeah. Oh, nice, nice. I like it. I like it. Oh, what is that? That's so weird. My phone's talking to me. Sorry. Hello, Audrey. How are you?
I'm good. How are you?
Good. Good. I'm sort of getting this this whole video thing together. I mean, this is like in the hands of. I mean, I'm a chemist. I'm not a computer science person. I'm not a video person. Right, Brian? Although here's my valve. I have a cool looking valve called a selection valve. We're gonna put it on a oh, here I can put it on my webcam and then switch to webcam view. There we go. See, there's my valve. Swage lock. And so I think oh God, I'm not going to say it. Otherwise I'll jinx myself, but it seems like I'm sort of getting this figured out. But I had to switch computers because this headset that I'm using, it did not work with my new computer. Anyway, I'm just confused. So let's see. Let me go back to. So this is just a Chrome window, and that's as big as this stuff is going to get. Can you guys read it? Can you read this text
I
here?
can. I don't know if everyone else can though.
I can read it too.
Okay.
Same.
All right. Ah, Shiming can't find the link. Let me see. I've got to get him the link.
The link is on, if you go to the syllabus, it's the last bullet point above the schedule.
Yes.
I just put the link in our Slack.
Thank you. Can somebody put it into the message, the Zoom message thingy? I could probably do that, huh? Let's see here. I go Alt H, right, for messages. Alt H. Woohoo! Alt H, and then I'm gonna grab it from the syllabus from right here, along with some other junk, and then I'm gonna paste it in here. Oh, but that's not gonna help. That's only for people on the stupid Zoom call. Already, that's not gonna help. That's completely idiotic. Right? Right, Raymond? Was that an idiotic thing to do?
Maybe.
Yeah, maybe. Maybe. I think it was. Okay. So, so I got to get Qiming, and it is colon slash slash SJSU.
Hello.
Hi, Roger.
Hello. You made it.
Yes.
I'm trying to figure out how to type forward slashes on my stupid phone. J, another forward slash. J slash 836435. 836435. 25904. 25904. Okay, so I slacked it to Ximing, and I don't know what the hell that's going to do. Oh, it looks like we got almost everybody here.
I let them know.
Oh, good, good. Thank you. Because I've been freaking out about this since yesterday, but like I've had so many things to freak out about that this was like on the low level freak out.
Oh, but I'm not so sure whether everyone are now in this room or not. So maybe I should go back and check.
All right.
Yeah,
Oh,
yeah.
please
Okay.
go back and check. Please, please. Yes. Yeah. Okay, we got one more. We got. So I'm gonna figure out how many of us are here. We got 1, 2, 3, 4, 5. We got 25 people now, myself included. So I think we're missing 1 or 2 people. Oops. Oh, you know what I just found? I just found my chart of the nuclides, which is my favorite periodic table in the whole world.
It seems nobody is in that Zoom link. So I think, yeah. Now, how many? So still another one? Like 25 students now.
That's a periodic table. That's just an ordinary one. then if you want to see all the nuclides, then you got to go to the next pages. Oh, and actually what I can do is I can switch to my document camera, right? And I'll take my very cool swage lock selection valve out of the picture, and then we can go to here, right? And we can look at some isotopes. There's hydrogen, there's deuterium and tritium, right? These are the three isotopes of hydrogen. Oh, and there's a neutron, right? Oh, that's wild, huh? They got the neutron there. It is Z equals 0. Isn't that wild? You can even get the neutron on the chart of the nuclides. And the half-life that they give here is 10.5 minutes. That's wild. So outside of the nucleus, you guys, the neutron only lasts 10 minutes. And it decays into a proton, an electron, and a neutrino, I think. Pretty sure that's the fate of it, right? And then we got then there's some weird. Now these are mostly stable nuclei, and these ones off to the side are in the like beryllium 6, and I think they're fairly uncommon. But there's carbon 14, right? And carbon 14 is has a half-life of 5,730 years, and it decays by beta, right? So if the carbon nucleus ejects an electron, it goes by beta minus, right? Then it's going to convert one of its neutrons into a proton, right? One of the neutrons is going to create an electron, and then, well, I don't know, something like that, and then that thing will become a nitrogen 15, right? Which has a half-life of 0.37 seconds. And I'm not sure how it decays. Oh, no. Nitrogen 15 is stable. It's stable. It's gray, right? So carbon 14 makes nitrogen 15, right? 99.63% of the nitrogen in the world is nitrogen 14 in our world, right? But then 0.37% is nitrogen 15.
Wait, excuse me?
Yeah. So nitrogen. Yes. Go ahead.
I was just gonna say, if it was a neutron converting into a proton, would it be nitrogen 14? I mean, correct me if I'm wrong, but I just thought that since you're getting rid of
Oh, you're right. You're absolutely right. You're absolutely right. It creates nitrogen 14. It goes diagonally, right? Because it takes away from this one, but it adds to this one, right? There you go. You see, you guys are smart. I need you guys. Keep after me here. Okay, so let's continue on with this general trend here. I drew you a picture. This is my original artwork, and it is available. Signed copies are available for $10,000. I'm just kidding. But anyway, so this here is a uranium atom, right? And it's about a half a nanometer in diameter. And you would designate it by 92, 235, pretty sure there. And then, then you'd put a U, right? And I just said atom there, right? And then if you zoom in about 1,000 times, you'll see the nucleus. I think it's 1,000 or 10,000 times. Right? And then there's the nucleus, and that nucleus can spit out an alpha particle, which is has 2 positive charges and 2 neutrons, right? And then that'll leave a 290 nucleus, right? I'm sorry. What am I saying here? This would be 235 minus 4 is 231, right? 231, right? So what nucleus will this become? So to answer that, we've got to go to basically it'll turn into thorium, right? Because it's uranium, protactinium, and thorium, right? So this will be thorium 231. Now, I don't think that that the uranium isn't even U-235 is not very radioactive. It's like got a billion-year half-life or something. So I'm not saying this is a common reaction. It's just an example of what can happen, right? So anyway, that's how we sort of move around the periodic table, or rather the chart of the nuclides here. And then if we want to know the energy associated with those processes, then we need to use a formula like this, right? Delta M. Okay, now let's make sure I got this one right. So MP. Oh, so this is the mass defect, right, in a given nucleus, right? So this is, if you know the mass of the nuclide, right, you know the mass of the nucleus of the atom that you're talking about. So you got to be clear here that you have to take out all the electron masses. Then you can say, well, the theoretical mass here, which is Z times the mass of the proton, plus A minus Z times the mass of the neutron. So this is the number of protons times the mass, the number of neutrons times the neutron. This is the theoretical mass. This is the actual mass of the nucleus. That gives the nuclear mass defect, delta M. And then delta M times C squared is delta E, right? That tells you how much energy is liberated for every nuclide that we create. So, so let us calculate using this formula the energy for the following 2 processes. The fusion of 2 deuterons to form helium, and then the bonding of 2 deuterons to form deuterium gas, right? And it's slightly different, but not very different from the delta HF of hydrogen gas, right? Which is 218 kilojoules per mole. So that basically, I gave that one away, right? You can just look it up. And actually, this should probably be minus 218 kilojoules per mole. So what I would like to try now is I'm going to try to put you guys into little breakout rooms, right? And I'm going to create 5 breakout rooms, and I'm going to assign us all automatically. Boom. I'm going to open these rooms. right? And I'm going to broadcast a message. Oops. Broadcast a message. And can you guys see the rooms that you're supposed to go to now?
Yep.
Like on your Zoom things?
Yeah.
Okay. So we're going to have a contest to see who can compute the energy for the fusion of two deuterons to form helium-4. Right? That's and basically the way you're going to do this is that you're going to calculate the mass of the products and subtract the mass of the reactants, multiply that by c squared, and that will be the energy released, right? So you can take the M nucleus for the deuterons, 2 times the deuterium mass nuclear masses, minus the helium nuclear mass, multiply that by c squared, and that will give you an energy. And that energy is the energy that will be released when this fusion event happens. So this guy here, I guess we could probably 2 times two. C squared is the answer, yeah? Okay. Does that make sense?
I'm sorry, what's a deuteron?
Oh, a deuteron? Deuteron is it's an isotope of hydrogen, and it's got 1 proton and 1 neutron,
Oh, okay.
right? So the deuteron mass we can look up, right? So here, I actually did it here, but I don't want to give it all away, right? Okay, this is how to compute the heat of formation of the H2 molecule, right? And this is just turning it into electron volts here. But let's go to the fusion one here. And then you can use the mass of the deuteron and the mass of the helium atom here, right? But I don't want you guys to cheat. I want you to calculate it. So I'm going to copy this. And I'll put that here. There we go. So the deuterons, 2 times the deuteron mass is significantly more than the helium mass, right? But when the 2
I just wanted,
deuterons, yes.
your screen's very blurry and I can't read anything on it. And everyone in the chat's saying the same thing. So just letting you know.
Oh shit. Okay. All right. So are you guys in rooms yet or no?
No, we're not in
No.
room. Well, we were assigned rooms, but I don't think anyone.
Okay. No one has left for the room. Okay, got it. So my screen is blurry.
Did you
Damn it.
open
I
some
don't-
effect or something?
No, I didn't open an effect.
It looks like painting,
it looks like what?
like a painting effect or something.
Okay. We're gonna have a beer later, and you're gonna tell me what you mean by that. Let's see here. Looks like a panty effect. Let's see here. So, hmm. It's so weird because it's supposed to be 2560 by 1440, right? Maybe I can canvas it this way. Is that better?
Nothing changed, I think.
Nothing changed. Thank you. Okay. Okay.
I think we can just use the slides on the computer.
Sorry. If I can just use the what?
I think we'll be fine just using the slides on our own computer, like opening it up on our own computer.
Oh, there you go. There you go. That might be better. That might be better. Oh, God.
Oh, Roger,
So I think there's 19.
I can share the screen, and I think they can see the change on the slides, right? So if I share the
Uh-huh.
slides of yours, oh, but
Well,
could you
I think everybody can access the Google Slides, I think, directly, or you can share yours. That's fine too. But in the beginning, it was clear, and now it isn't. What's going on? Is my computer overheating or something?
or maybe try to
No.
like reload.
Yeah. That is
Start the
so
camera.
weird. Right. Okay. Okay. Well, I'm going to stop it and then I'm going to restart it. Okay. So now it just should show a weird thing, like a little. Now, if I start it again, is it any better now? It's the same crap.
This is
Yeah.
The same.
Same old, the same. Okay. All right. Okay. Ah. Let's see here. I don't know what to do. I'm sort of okay, I think I know what I can do here. I am going to go to Zoom. And I'm going to tell Zoom that I don't want my OBS camera on here anymore. And I want to share my screen. And I want to share this screen.
Yep.
Better?
Ah, yes.
Okay. 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 Good. All right. OBS is now fired for inconsistent performance. And I'm going to try to share myself here. Okay. Oh, so now I got to go up here. I got to start my video. So now you should be able to see me somewhere, probably up in the corner, and then this thing. So let's get calculating. Go to your room and see if you can calculate the energy of a fusion reaction. Oops, that didn't work. The energy of a fusion reaction. Oh man. There I am. How do I make you guys go to your rooms? Oh, looks like you're sort of filtering in there.
Yeah, everyone has to click breakout on the bottom and join room.
Okay. Thank you. Thank you. Yay, breakout, join room. Okay, so the three of us are left. So now we just wait and we have a chat and we make fun of the students while they sweat. Yeah, a bunch of losers. I'm just kidding. Just kidding. So, do you think that the outcome of this calculation for the fusion reaction will be greater than the heat of reaction for the formation of deuterium D2? Or will it be small in absolute magnitude? Will it be smaller?
You mean comparing with the formation energy?
Right, right. Yeah, if you take two deuterium atoms and you just let them make D2, they form the chemical bond, versus smashing the nuclei together such that the nuclei form a helium atom. Which of those two will have a greater heat of reaction?
I think fission will have greater one.
What will have a greater one?
The fission.
The fusion, right,
Oh, the
right,
fusion.
right, right.
The fusion.
Yes, exactly. And the factor, it turns out, is like it's like a factor of 100 million or something. So you know how that you can take an energetic chemical reaction, and almost any nuclear reaction will be 1,000,000 times more energetic. Right? That's why people are really seriously reconsidering nuclear propulsion for spacecraft.
Oh, that's
Yeah.
difficult.
Yes, it is. Yes, it is. And it can be extremely messy. And so far, their best concept, you guys, is to have the fuel in tubes, in like a long tube.
Yeah.
Right? And you have a fissile isotope in a long tube, and then you shoot it out a nozzle, and the nozzle expands, right?
Yeah.
And as the nuclides come out of the tube into the nozzle, their geometry changes and they become supercritical, right? When they're in this thin tube, then they don't share neutrons, right? If one of them gives off a neutron or something, who cares, right? Because they're most likely lost, right? So that is a subcritical arrangement. But if they expand into a nozzle, then that even though they're expanding and becoming further apart, there are now nuclides in 3 dimensions, and then that naturally heats up, and it goes supercritical, or it goes probably prompt. There's different levels. There's supercritical is when it explodes, and so it goes prompt critical, and that's what we're looking for here. Alrighty, so I'm gonna visit a room here. How do I visit? Okay, I'm gonna join room 1.
Yeah, you can jump around. Yeah.
Hey guys, any progress?
Well, I made some progress, but I'm kind of stuck on the C constant.
Oh, C is 3 times 10 to the 8th meters per second.
Right. But then I was also thinking like how the atomic mass unit is like,
Oh, you have to change it to kilograms.
right.
Right.
Okay.
So carbon 12 is the easiest one, right? So you can take an AMU is 1/12 of the weight of a carbon 12, right? So you just need Avogadro's number. And let me change my camera out here. I'll give you some support. Let's see here. I'm going to change to my webcam. All right. Can you see my document camera now or no? You just see my stupid face, right?
Yeah,
I
I
see
see.
your
Oh.
profile picture.
Okay. That's a much more polite way of saying my stupid face. Thank you. Let's see here. Okay, so I'm gonna use my document camera then, or I'm gonna use my regular camera. You can say that the mass in kilograms is equal to the mass in AMU times oh wait, how do we do that? It's the mass in AMU divided by the mole, right? So it's mass in AMU divided by I want to get my units right though. Mass in kilograms. It's equal to say 12.000 AMU times 6.023, oops, times 1 kilogram. I think it's like this.
So we
It's like a
convert
gram.
AMU
Mhm.
to
AMU to kilograms, yeah.
right. And then we convert kilograms to grams.
hmm Yeah, well, you convert grams to kilograms,
Right. Okay. Yeah.
right? Does that look right? So then we'll get, so for a deuterium, right? D2, actually the mass of deuterium, we can look that up, but I think it's in the, it's in the Google sheet, right? Ah,
I saw it in the
So
slides.
the,
Right.
right, 2.014, right?
Mhm.
So it's 2.014 grams per mole, right? And then we multiply that by a mole in 6.023 times 10 to the 23rd, right? And then 1 kilogram for every 1,000 grams, right? And now we're getting back on the right basis. So that'd be the mass of in kilograms of the deuterium, of one deuterium atom. Right, it's super small, but at least we've got a kilogram mass for deuterium, right? For deuterium atom. And then we can scale up. We'll probably end up multiplying by Avogadro's number again, just because I'm stupid. But
Yeah, I think
this
that's
should,
it.
yeah. Okay. Okay. Good. So so let's go ahead and see. Basically, we got to get the delta M for these two guys. Multiply that, change it to kilograms, multiply it by C squared, and that will give us delta E per nucleus, per pair of deuteriums that fuse, right? And then we can multiply that up to a gram scale or whatever we want to, right? Or we can just leave it there and then we can get the other one, because ultimately we're going to be comparing the chemical energy to the nuclear energy. Yeah.
Yeah.
Okay.
Yeah.
Okay. Cool. All right. I'm going to leave and I'm going to bother other students. Wow, it is so wild because I have this ginormous TV. I'm sitting in front of this ginormous TV, and when Zoom takes over, it like fills the whole TV. So somebody's face will be like, blah. All right. So, Astra, how did it go?
It went pretty well. I think
Uh-huh.
100% confident in our answer, but I mean,
Okay, you got 95% confidence, maybe?
a little less.
All right, cool. And so Astra, Vivian, how did yours go, Vivian? Are you guys from the same breakout group? Okay, cool. So tell me this. You guys are the first, right? So you're gonna get you're vying for first prize here. And my question to you is, did you get um, uh, 3.8 times 10 to the minus 12 joules? Uh-oh. What did you get?
Oh, was that for the first or for the second part?
3.8 times 10 to the minus 12 is joules per pair of deuterium that That's the joules per reaction, per pair of deuteriums that fuse, or per single helium that's formed. Does one of you want to show me your calculations? You can just show me like that if you want. Rachel? No? No? Audrey? No? Vivian? Not no, but hell no. Sadana? No? Astra? No? Nobody's going to show me their calculations? Okay, tell me what you got, though. Tell me what answer you got. I'm going to write it down. And what unit you got it in, okay? Okay, so not going to tell me. Nobody's going to tell me. Everybody's muted. But you're very courageously leaving your cameras on, however, that's good. Okay. So I'm going to have to visit another freaking breakout room. I'm going to have to visit another breakout room. So I'm going to see how other folks are doing. Here's the rubber hitting the road right here. I'm assuming too much. It actually takes a while to get through these kind of calculations, right? But I can show you, like, for example, this is how you get the, oops. That is so weird. That's how you get the number of kilograms per deuterium. It's not D2, it's just D, right? It's 1, 2. It's deuterium. That'll give you the mass of one of the deuteriums, right? Then you subtract out, you multiply that by 2, subtract out the mass of the helium, then there should be a positive mass defect, and that positive mass all turns into energy. And the energy, it's basically kinetic energy of the particles when they're done. That is the energy of the explosion that happens when you fuse two hydrogens. Yes? Okay, cool. All right, so I'm going to visit yet another breakout room, maybe. I don't even know what I'm doing. So breakout rooms. Okay. I'm going to join room 2. Hello, how are you?
Good.
How is the progress? No progress?
I think we have answers.
You have answers. Excellent. Show me your answers.
I think like Alicia has an answer and I have an answer that also maybe, or it's different, but I think mine is probably wrong. So I'm just trying to figure out why right now.
Oh, okay. All righty. So Alicia, share your answer with me. Ah, I love it. Right. All right. So that is right. That is perfect. Perfect. 3.83 times 10 minus 13 joules per nucleus, right? Per pair of atoms that react, right? So now what we want to do is we want to convert that into, well, actually, we can leave it there. I actually like to think about it in another unit called electron volts. Okay, so the EV, let me see if I can find a good way to do EVs for you. I don't think I can, I don't know how to share my screen with a group. So, maybe I can do this. Nope, can't do that. Nope, can't do that. I can't do anything. Okay, so let me figure it out here. Oh, there's just a straight conversion. It's 6.2 times 10 to the 18th electron volts per joule. So you get 3.8 times 10 to the minus 12 EV per helium nucleus, right? And you multiply that guy by 6.24 times 10 to the plus 18 EV per joule. And that gives you 23.8 MeV. Right? Okay, good. Alicia says yes. Raymond, can you show me your calculations?
Oh wait, I didn't write them down. I think I just like used the wrong number for like avocado or something.
Okay, got it. Okay, all right. And Kita, how are you doing?
I wasn't sure how to do it, so I mean, I tried doing something. But didn't do it.
I wish I'm trying to get you guys to like work together, but it's not working. It's not working. We don't have a way to share a workspace, you know? So, so here, let me just do this. Delta M is equal to the mass of the helium minus the mass of the deuteriums times 2. Whoops. Because 2 deuteriums, they fuse into one helium. And then that value times c squared is equal to delta E. M equals mc squared, right? Yeah? Cool. This is where it comes from. Actually, no, E equals mc squared. It was calculated theoretically by Einstein in his special relativity paper around 1901 or early 1900s. And he just came up with it theoretically. He says, oh, and by the way, E should equal mc squared. It's like, oh, no big deal. And anyway, so you get that one, and then you should be able to get to, then you can multiply by, you should get this. Oops. It's so confusing for me because everything left is right and up is down. Everything flat is bent. Okay, cool. I'm gonna sign off, and I'm gonna visit another room. Did you get that, Ankita?
Yeah.
Okay, good. Okay, cool. Rohan, how are you doing, buddy?
I was also lost. I mean, I like chemistry. That one threw me off. So that also helped. I
Okay,
saw it.
got it. All right. It's all units and stuff, you know, and basically understanding that it's like this is thermodynamics, right? This is basically just take the products minus the reactants, assume they have some constant internal energy, then the difference between them should be the energy given off in the reaction, right? That's all we're doing. You know, we're not considering pressure, temperature, volume, or anything. Just internal energy change. Yeah. All right. I'll let you work on that, and I got to visit another couple of breakout rooms here. Let's see here. Hello. How's it going?
Good. We did whatchamacallit, number 1. I think we're
Yes.
kind of stumped on number 2, and we were
Oh,
just
okay. Okay. Cool. So, what did you get to answer number 1?
We got 3.82 times 10 to the negative 12.
Ah, yes. 10 minus 12th joules, right?
Yeah. And then
Excellent. Perfect.
number 2, I'm not
Yes.
sure if I did the right thing. But
Yes.
I got 5.31 times 10 to the negative 16.
Times 10 to the minus 3?
Negative 16.
16. That sounds close. Yeah. So now divide them. Put the minus 12 in the numerator and the minus 16 in the denominator, and then see what you get. And I think you should get something like 200 million. What did you get? Or you haven't done the second one. Is that what's going on?
Like, we didn't really do it properly, I think. I just kind of.
Oh, okay. Sorry.
I don't think we really get how to do the second one that much.
Oh, okay. So second one is basically just it's basically 2 times the enthalpy of formation of a hydrogen atom. So the enthalpy of formation of a hydrogen atom, or the energy of formation of a hydrogen atom, is it's non-zero because the standard state for hydrogen is H2. So the standard energy for H2 is 0. So the standard energy for the 2 hydrogen atoms will be non-zero, and it'll be some large positive value, right? So there's a large energy change when you put them together. And I forget what the values are here. Let me get the values for you just real quick. So I get 4.5 EV, or 436 kilojoules per mole. Yeah, because the the heat of formation of a single hydrogen atom is 218 kilojoules per mole. So I'm just approximating deuterium and hydrogen right there, right? So I just looked it up. I just sort of like Googled it. I'm up with you guys now. You guys can't, for years, you guys have been kicking my butt. Because I say, oh, you know, and we've got to calculate this and this. And then somebody goes, and they look it up on Google, and there it is. Could probably do it with this problem too. But that would be cheating. So anyway, the so I got 436 kilojoules per mole.
Oh, because you did just two. So it's just 2 times 218.
Right. Yeah. Basically, because you've got the two entities are hydrogen plus hydrogen make H2, right?
Mm-hmm.
And H2 is 0, so the total reaction energy is just 2 times the reactants minus 0, right?
Mm-hmm.
So products minus reactants, it'll be 0 minus 2 times 218. It'll be minus 436 kilojoules per mole, right? And whatever unit you got the other one in, you've got to get a common basis of units to do the comparison, right?
Mm-hmm.
So I converted them all into electron volts, but you can do it in joules or whatever you want to do, and the answer should come out to be 5 million, 5.2 million. All right. So see if you can get 5.2 times 10 to the 6th out of this. This will be the delta H for the fusion minus delta H for the chemical reaction. Where am I? Here I am. Ah, there I am. 5 times 10 to the 6. 4.5. Oh wait, yeah, 5.2 times 10 to the 6. Right. Don't be confused by the H. Any way you calculate energy is fine. All right. Cool. So I'm going to visit another room, and I will be. Oops. Oh, okay. So I think everybody's gone back to the main stupid Cosmos thingy room. Okay, close all rooms. Closing rooms. Bye.
Goodbye.
Okay, so that was a gigantic failure, right? But I tried. You cannot say I didn't try. But let's see here. Let me go back to sharing my screen. There we go. So so I got 23.8 megavolts for the fusion and 4 volts for the chemical reaction, right? And electron volts and like volts in a battery, they're the same thing, right? So it's kind of cool that way, right? So you can say like, if you had a way of like, you know, electrochemically coupling the energy from a fusion reaction, you'd have a 23 million volt battery. I have no idea how you would do that. Let's see here. And I have a few more of you. Oh my gosh. Okay. All right. So, so let's go back to the notes here, right? And let's just say, okay, so I did one for you on this next one, which is the comparing a carbon-carbon bond dissociation energy to the mass defect in forming a carbon atom, right? So that's just take the mass of the electrons plus the mass of the protons plus the mass of the neutrons, saying, okay, how much does the carbon atom weigh? Get the mass defect for the carbon atom, and then calculate and then compare that to the formation of a carbon-carbon bond, right? And that guy there, that came out to 237 million. So that's not really fair because that's a whole bunch of protons coming together. But you can see how for light atoms, when you fuse them together, the products weigh less than the reactants, right? And that is called the mass defect. And that mass defect tells you where you are in the binding forces for the nucleus, right? So as you build up nuclei and you fuse these particles together, they weigh, going up here is where they're losing weight as they fuse together, right? But when you get to iron 56, then it starts to cost energy to add more protons and neutrons to the nucleus, right? So it starts to come down into this endothermic regime, right? Somebody tell me what I just said. Lucas.
You're saying that as there's more heavier elements combining, that they lose, essentially, it costs them energy to bond together.
Right. And now this is nuclear energy, right? So it's when the nuclei fuse, obviously, yeah. So what is the most stable nucleus in the periodic table according to this Max?
Iron 56.
Okay,
Or
cool,
actually,
Lucas.
no. Or
Thank
would
you.
it be hydrogen because it's so low?
No. The most stable nucleus is iron 56. It's the highest one, highest binding energy per nucleon. It's the most energy loss you can get per nucleon is when you make iron 56, right? If you add nucleons, if you add protons basically plus some, appropriate number of neutrons, then the whole nucleus gets less and less stable. So the most stable nucleus is iron 56, right? So if you're a star, where do you get your energy? I mean, not a star like Michael Jackson was a star, more like a star like the sun is a star. So where does the sun get its energy? Fusion, exactly. Fusion of what?
Hydrogen, helium. No hydrogen, just hydrogen.
Yes.
And helium.
Hydrogen.
Up to oxygen.
Hydrogen and helium and stuff like that. Exactly. It's going up this hill, right? Boom. It's who knows what's really going on in there, but hypothetically, most of the fusion in our sun right now is hydrogen, right? And so hydrogen is making helium, and Helium was first discovered in the sun spectrum, the heliosphere. So that's why they call it helium. Helios is sun, I guess. Anyway, so as the hydrogen depletes, right? Then the star goes on to another process, right? Which is fusing lithium and stuff and making carbon, right? And it can do that for many millions of years, right? But as it's doing that, it's cooling down, right? Because these fusion reactions are they're not as extremely exothermic as these ones, right? Right? And so after you make oxygen, you start making these things. When you get to iron 56, nothing happens anymore, period. The star dies. And when the star dies, something happens. I know I'm talking riddles here, right? But then the star, when the fusion reactions stop, then gravitation takes over and the star starts to shrink, right? And then as it shrinks down really, really small, then you start getting well, it's complicated, right? There's things that happen in the mantle of exploding gases, but most of these heavier nuclei are created in that supernova explosion that happens when all the components of the star crunch down into this small mass. And then boom, there's a secondary explosion as all this stuff fuses, and then you get a bunch of heavier atoms, right? So all of the uranium, all of the metals, all of the very fun stuff we get to play with as humans was created for us in a stellar nova, right? And it's all endothermic stuff, right? And now when we split U-235 to make barium and other stuff, we're just getting a little bit of that energy back, right? But I want to say something here, right? Which is that if we use up all the goddamn U-235, we are stuck on Earth. Because there's no way we're going to get anywhere near that amount of energy until we can learn how to fuse hydrogen, right? Once we're fusing hydrogen, then we've got another nuclear energy source. But I think it's important that as humans, the convenient energy sources are fission, right? You don't need to blast nuclei together at 100 million degrees. I mean, that may never work. It's never been proven so far. I mean, I hope I'm wrong, but it may never work, right? But on the other hand, fission is pretty efficient, right? And fission can get us off the planet and stuff like that. Anyway, end of sermon. But the thing is that there are renewables and there are non-renewables, right? The quote unquote renewable energy is solar energy from the sun, right? Which is photons that are given off by the sun, which are subsequent to the fusion of hydrogen into helium, right? These big 2.5 million electron volt processes, right? The more like 500,000 electron volt processes when you split U-235. They're what our nuclear reactors do, and they are not as energetic, even though they're still maybe 20 million times more energetic than a chemical bond, right? So who wants to build a nuclear rocket? Yay, I love it. Let's get off this rock. Let's fly around. Anyway, so now on to more mundane topics here. You know, the nucleus was discovered by Ernest Rutherford, basically. Ernest Rutherford and Marsden and Geiger, right? And then the electron was discovered by J.J. Thomson. And you know what I like most about these pictures, right? It's like the difference in the attitude of people whose pictures are being taken to the photographer, right? Because J.J. Thomson, he's looking at the sky. The guy taking his picture is going, "Stay still! Don't move! Don't move! Don't move! We're almost there! We almost have enough light to take your picture! Stay still!" And Thompson's like looking at him like, "What the bleep are you saying?" Right? That is what this face is saying, right? Rutherford, he knew what was going on, man. He got dressed up and he's like, and they're telling him to stay still, but he was like, "All right, dude, I'm getting my picture taken." He's even got a slight smile. This is before it was fashionable to smile in photographs, right? You notice none of the old photographs does anybody smile. Nobody. Everybody's so serious. It's kind of like you guys. Let's see here. So, so now there's a couple of guys here, Frederick Soddy and William Ramsey, and they both worked with Rutherford, right? But they discovered that alpha radiation are helium nuclei, and they did that with a really cool apparatus, which it's kind of like, it's a little bit obfuscated by this diagram, but basically this tube A in the middle here has xenon. It's full of xenon gas. So there's radium in it. Radium decays by alpha to make xenon. Xenon decays by alpha to make other stuff, right? So this tube is super hot radioactively, right? And the glass that tube is made of is super thin. It's like 10 microns. It's thick enough that none of the radon and none of the radium can get through. But the alpha particles that are shot off at high velocity, they break out of this tube, they go into this larger envelope, right? And then you set up an electrical discharge between V and this mercury down here. And then you look for the spectrum of the gas that's filling that tube. And what do you find? You find helium. And this was one of the first important discoveries of the 20th century. And it just kicked off a whole bunch of very fun stuff, right? Now, these guys also worked a little bit with Lord Kelvin. And this guy, his name is William Strutt, right? And he's an odd-looking guy, isn't he? I think it probably though the mutton chops and the mustache, they probably work for him, you know, because he might be kind of not so attractive without that, right? But this is Lord Kelvin, and then this is a guy named William Seeley Gossett, right? Now William Strutt became known as Lord Kelvin, right? They knighted him, they gave him a lordship, a shit ton of money, and all that good stuff, right? William Seeley worked for the Guinness Brewery, right? So William Seeley was a beer maker, and his pseudonym was Student, right? Professor and student. Get it? Kind of cool, right? And what what they did was together they discovered argon. Okay, now Davida will remember this because I bang on this, and it's in all the university chemistry textbooks, right? And what they did was they made air, or they made nitrogen using a chemical method. They had some azo compound, they broke it down, they made nitrogen, and they weighed the nitrogen that they made. They filled up a bulb, they got it to the right pressure, they closed the bulb off, and they weighed it, and they got 2.3 grams, right? They actually got this distribution of weights. Right? And then they weighed a bunch of air, and they got a much tighter distribution. But the air was heavier. I'm sorry. They got nitrogen from air, right? So they took air and they removed the carbon dioxide, and they removed the oxygen and the water. So you can dry air out, you can do all this so that you only have nitrogen left over in the air, right? Because air is oxygen, nitrogen, carbon dioxide, and water vapor, right? But these weigh a different amount, right? Nitrogen from air and chemically generated nitrogen, they weigh a different amount. Why is that?
Because there was something
Let me see
else
who's
in the
awake.
Oh, is it? Oh.
Yes, yes, exactly. There was something else in the air. There is neon, argon, krypton, and xenon, right? But the only one in any significant amounts in air is argon, right? So the difference between these two weights proved that there's other stuff in the air, and it turned out to be argon, right? Now, how did these guys figure this out? Well, this is where the beer drinker comes in. The beer drinker, he established the statistics of measuring sugar in beer so that you get the right taste, right? And he calculated this statistic called T. T takes the difference between two measurements, divides it by their standard deviation, and multiplies it by the numbers of specimens in each pool, right? And then this is how you get the standard deviation for the pool, is you sum each measurement minus its average. You square up each of those. You add it to the second set, square them, right? Add them all up, divide them by the degrees of freedom, take the square root of that, right? And that gives you a S pooled, and then you take that. Now you take, and you can divide this out, and you get a statistic called T. And T belongs to a universal distribution, right? T is a universal quality for random data sets, right? Once you take a data set and you divide it by the standard deviation, subtract out the mean divided by the standard deviation, you always get one of these funky dunky looking distributions, right? The green one is called the normal distribution, right? That's the one you get after you've measured it 100,000 times. And in this case, the value of the observation is going to be 0 here, right? This is it's like the value minus its own average, right? And the probability of observing that is the highest when you're at the average, right? Then as you deviate from that, the probability goes down, and it goes down pretty darn fast. As a matter of fact, it goes down as e to the minus x squared. E to the minus x squared, right? So the x is squared, so it declines on both sides really quickly. E to the minus x squared, right? E to the minus x squared makes this normal distribution, right? Now, Gossett came up with a way to calculate this for small data sets, right? So he took these, and you can generate a t-distribution for each of these data sets, and you can ask how much those distributions overlap. And to make a long story short, you can calculate this using Excel, for example. You get the mean 2.31, 2.29, take the standard deviations, the difference, da 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 da. And that guy comes out to be, I have it here. Oops. Let's see here. Make sure. Let's see here. Let's go right here. And that probability comes out to 8 times 10 to the minus 8. Right? And what this means is that given these data together and these data together, the probability that those two groups of data are from the same origin, right? They all have the same mean value. Just these are higher by chance, these are lower by chance, right? The probability that they're the same is approximately 10 to the minus 7th, right? So 1 in 10 million times, you'll get this population and this population with these standard deviations from replicate measurements of the same thing. Yeah? So this means they're different. Because that number is so small, the only reasonable answer is, well, they're different. Right? And this is the t-test. This is the Excel t-test. So why don't you guys maybe you guys can work on this a little bit tonight during your transferable skills stuff. Alrighty, are we cooked? Have we had enough for today? Possibly?
My brain is fried.
Good. All right. This is your brain on Cosmos. You guys that reference is so old now that nobody even gets it. But they used to tell us not to take drugs. And that what they would do is they would show a picture of an egg being fried really hot on a pan, bubbling, and say, "This is your brain on drugs." Say, "Oh no, it's my brain on drugs." But, so this is our brain on Cosmos, actually. Okay, guys, I'm done. I did not cover nearly what I wanted to cover today because I don't know how to use breakout rooms. But it'll be better next time, I guarantee. Every day we're going to get better. All righty.
I think it'd also be helpful if either today or next time you could go over the computations for determining the energy with mass defect, because I know there were a lot of
Okay.
There's a lot of uncertainty looming around that one.
Okay, perfect. I will do it. You know, it's like, this is a classic case where I'm a shitty teacher, right? I just cannot teach this because to me it's like blindingly obvious. You know? It's like saying, you know, the sky is blue, look, you know? But like, if you don't know what blue is, you don't know what the sky is, you don't know what look means, you know, it doesn't make sense, right? So I am a shitty teacher and I will go over those calculations next time. And I'll just make up something so that you guys can see it in print, right? Rather than listen to me talk about it. Thank you. That's a great suggestion. Thank you. Okay, guys. See you tomorrow.
Thank you
I
so
think
much.